So, hey guys, I'm Yash. I'm a first year student at the Department of Maths in IIT Bombay. I was in INMA awardee this year, and my college has just begun this month. I mean, it's already been a month, and I'm very excited to meet you guys, do some NT today. So, this class will be on different techniques in NT. Now, of course, there isn't a finite list of techniques that you can just try and solve a problem, but there are quite a few. Good things that you might encounter and very few very fun problems that you will see today. So let us begin. So I'll start by saying what local ideas actually mean. So often say in NT you're given a random function of multiple variables and you've been given a certain freedom to choose what coefficients they have or like what powers they have. So often there's no nice closed form for them, like for the sum that you are evaluating. However, if you see that if you swap, say, two variables, the quantity changes by a good amount. Or say if I've been looking to find a good permutation that has a certain value, then say I pick a random permutation and then I say make a circular shift and see what the quantity changes by. Often, you can see quantity changes by a finite number of terms, and if say you're working mod primes, then you can make that quantity be equal to anything you desire. So there's often ideas like that, and then there's discrete continuity. So there are problems relating to those ideas as well, but this might be a longer session. So I'll start off with discrete continuity today. And discrete continuity precisely is a discrete version of the normal continuity you see. So here in the change between two function outputs is bounded by say a fixed constant or the growth order is such that you can find, say you're looking for the function to attain a certain good value, then you can start off with values much less than that and values much bigger than that. And then if the function increments at bounded values, then you might hit something in a very good neighborhood of that good value. So I'll just give off an example. It looks like very fun, like on the face. So you all know what does pi n mean? It means the prime counting function. So are you guys aware of the prime number theorem or something of that sort?
Yeah. It's just like I guess it was the number of primes before n is n log n.
Yeah,
But
yeah, yeah. N by log n, right?
n by log n.
Yeah. So now I give to you this very wonderful statement that there exists infinitely many n such that pi n divides n. You can think about it for a minute and come up with say ideas. I've pointed out discrete continuity in some sense, so try thinking in that direction.
Does phi of n include n also, or it is like the numbers before n?
I mean, for our purposes, it won't matter, but you can think of it as the number of primes less than equal to n. So yeah, it might include n.
Okay.
Any ideas, like anything? Basically, pi n divides n for infinitely many n. That is the proposition.
Can we just start like considering n as prime so that we can get some ideas?
Wait, prime often works when you're like considering the divisor on the LHS, right? I'm not saying for all large n's, so you cannot characterize pi n very nicely, like from the prime number theorem and further studies, you know that it's not that characterizable. So it's something about the size of pi n and not exactly the property that it counts the functions. That's another hint.
Okay.
Okay, I like write the first line of the thing. So you can give any comments if you find it intuitive or not. So consider the thing n minus k n k pi n for some natural k. Okay, so all you're wanting is that uh, you want this equation to be zero, right? For some k,
Yeah.
for some k comma n, right?
Yeah. Yeah.
Uh,
Right.
so now, right, like you know of the intermediate value property, right? If the function is negative and positive, it is zero at some point. So
Yeah.
try thinking like that. Like increments of this function. Look at increments of this function. Also, guys, let me know like if you don't find this statement unintuitive. I'll try to motivate it maybe.
No, it's like it's okay up to n minus natural number k phi of n being zero, but after
Yeah.
that, like how to think about this?
So basically, if I can choose multiple keys, I'll get different ends, right? And that proves the thing,
Yeah, so if we choose different case, we will get different ends, right? So
right?
how
I
can we
mean,
like, yeah,
yeah.
how can we say that for a k there exists any n?
No, I'm asking you to find like, is there a good K for which that there might exist such a thing? And like, I'm asking you to look at increments of this function.
What exactly do you mean by increment? Sorry, could you?
Say if this function is like gn, then I'm asking you to compute gn plus one minus gn.
Okay.
Guys, at least tell me what the increment is. It's not that bad.
Like the function would increase 1 or 1 minus k.
Yes. I mean, not 1 minus k. 1 minus k, yeah, something negative, right? 1 minus k. Like k into something
Yeah,
positive, right? Because pi n plus 1 is non-decreasing, right?
yeah,
So it can increase by at most 1. Do you agree with that? It is 1 minus, like the increment is precisely 1 minus k into pi of n plus 1 minus pi n, right? You agree?
Yes.
Yes.
This is non-negative.
Yes.
So this entire thing is less than equal to 1, right? And it's an integer.
Okay, right. So it can be like negative or zero.
Yeah, right. So basically now if I fix my n, like I start at a small value of n, say 3, and I consider 3 minus k by 3, I choose k very large negative such that this quantity at 3, like g of 3 is negative. You see that, like I can choose any k that is large enough, right?
Two. Case two works.
Yeah, I mean anything works, right?
Yeah.
And then do you agree that eventually this function gn, as I make n large, this will be positive for a fixed k, of course.
And large. Yeah, right.
See, that is because you know that, okay, if I vaguely write that the limit of like n by log n by n is 0, right? Log n is unbounded, like limit n tending to infinity is 0, right?
Yeah, works.
Yeah, so basically what I'm saying is that n minus k pi n is eventually positive. You can just write this inequality, and it's like it reduces to n minus pi n being greater than k. This is roughly, okay, I'm not introducing any like notation or something, but you know that this is roughly log n, right? Do you agree? This part.
Yeah. Yeah.
I mean, some constant time log n. It's at least some constant time log n, right?
Mm. Yes.
So,
Like
You know that
we can like
log n is unbounded, right?
your log n is less than something like that. And
Huh?
by unbounded you mean log n should be less than n.
No, no, no. By unbounded, I mean that log n takes arbitrary large values. If I increase my n,
Okay. Yeah. Works. Yeah.
you agree with that?
Yeah.
So you see that this is eventually positive. As I make n large, this becomes positive. If I start with a fixed k, right?
Okay. Yeah.
But initially this function at g3 was negative. Agreed.
Hmm.
For some large n naught, g n naught is positive. My
Yeah.
function increments by at most 1. You agree?
Okay. So yeah, there it should
So
be
it
zero.
will hit 0. It will hit 0,
Works. Yes.
right?
Hmm. Got it.
So basically now I just vary the k. Like I can just choose large cases that the initial quantities are negative. And then for each k, I'll get a distinct n. Agreed? Because of course, like, uh, I mean, n by pi n is a fixed value, right?
Got it.
So basically, if I vary my k, I'll get infinitely many n.
but I did not understand how gn would be greater than 0 for some n naught.
Okay, right, I'm telling. So you agree that G3 is negative,
Yeah.
and there exists an n naught such that G n naught is positive.
Yeah.
So if my function increments by at most 1, like it is starting at something negative, and then at most I can increment it by 1, like it can say it can get plus 1 if I increase by n by 1.
Yeah.
That is the best it can do.
Yes.
So I will hit 0, no, if I go from negative to positive in integers.
Okay. Yes, I understand.
So now you get that desired n. And if I vary k, then I get different n, and that proves what I wanted. So it's a cool proof, right? You get it, no?
But why will it increase or decrease at most one?
That's what I was like. That's why I considered this is the increment, like pi n, like this gn plus 1 minus gn. At each step, like if I go from n to n plus 1, this is the increment, right?
Yes.
And this thing is non-negative, the inside the bracket thing.
Yes.
K is a natural number, so this is less than equal to 1, no?
Oh, all right.
Okay, so you guys got it, no?
Yes, sir.
Okay, so now you can generalize this actually. Bit like there was nothing special about pi n being the prime counting function. All we needed that it was sublinear. By sublinear, I mean the growth order. If I divide that by n, then I get 0 as the limit tends to infinity, right? I mean, I never used anything number theoretic about the prime counting function. Only the size thing, and of course the fact that it is non-decreasing. So basically, I saw this problem in a Bulgaria competition 3 to 4 days back. It is pretty much the same. So you have been given a sequence of natural numbers AI such that AI is again strictly increasing and AI is less than equal to I to the point 9. Okay. Then you basically have to prove that there exists infinitely many indices n such that an divides n. Can you see that this proceeds similar to the previous problem? This is a
Yeah,
sequence of integers, non-negative integers, that
yeah.
is strictly increasing.
It's like the same logic, right? Like in
Yeah,
n minus.
precisely. Like basically limit
Suppose
like I to the point 9 by I goes to 0 if I make I large. Like basically the only thing that I use is that uh, I use a different m minus k into am is greater than 0 if I fix k and if I make m large.
Yeah,
So again, you can use that discrete continuity argument since this is non-decreasing.
and we can again just check that increments by at most one.
Yeah. You have to check that, of course.
Yes.
So now the next problem might be a bit hard. So I'll build that up slowly. Like I'll build the theory. So you guys know about primitive roots?
Yes.
Yeah.
Yes.
yes.
Okay. So okay, I'll start off with a very important lemma. But before that, I'll probably write the topic name or something. Have any of you seen it before?
Yes.
Okay. So do you mind telling the proof?
Yes.
I don't remember
Okay.
exactly the
Okay.
proof.
Yeah. No problem. I'll write. Yeah. So basically, yeah. So you know that the property of a primitive root is that, wait, am I on it? Yeah. So the property of the primitive root is that g squared, g cubed, dot till g to the p minus 1 creates the entire residue set mod p, right? Like it's this is just a permutation of 1 to p minus 1, right?
Yeah.
So basically this sum can be rewritten as sigma, like I start off with some primitive root. I know that all i's are pretty much covered by powers of, like, if I vary, say, if I consider g n to the k p minus 1, then this is pretty much the above sum. You agree?
Yes.
So, okay, if I rearrange it a bit, then this is nothing but like 1 plus g to the 2k plus, uh, wait, g to the k plus g to the 2k till g to the p minus 2 into k. Agreed?
Then I think it should start from 0 less than equal to n.
No, p minus 1 is there, no? G to the p minus 1 is 1.
Oh, acha, okay.
And then this is just nothing but a geometric series. So this sum evaluates to g to the p minus 1 into k minus 1 by g to the k minus 1. Agreed?
Yes.
Are others also following?
Oh, yeah.
Okay, cool. So do you see that this denominator is non-zero if k is less than or equal to p minus 2? That's where the condition is important. Yeah, no problem. Also, preferably you can like unmute cause chat is a bit hard to see. So yeah, do you guys see why this condition is important? Because this makes the because this makes the denominator non-zero. Because the definition of the primitive root is that the smallest k for which g to the k is minus 1, sorry, is g to the k is equal to 1 mod p is p minus 1, right?
Yeah.
So if I take k less than or equal to p minus 2, this is non-zero, the denominator.
Yeah. So the whole thing becomes 0 mod p.
Yeah, this entire thing, because this part is nothing but 1 to the k minus 1. Okay?
Yeah.
Yeah. So can you guys think of a generalization of this, like mod prime powers? This is like an extremely important. I can give you a few problems. Okay, this class might be a bit above, like, I think RMO or LMO level, but specifically this problem, but okay. Any questions, please ask. So,
Like, what do you mean by the generalized version of it? I mean, I have used it in a lot of problems, but like, I didn't understand your question.
okay, so like I did it for prime powers. I get this is divisible by P.
Okay.
And like the numbers were pretty much the residue set mod P, right?
Yeah.
0 to P minus 1. Can you
Yeah.
think of it in terms of P to the K?
Okay.
The problem, like there was an initial problem at Atharv, and that was quite different. This one we are just building up. I haven't stated the problem statement yet. So any guesses?
Is it something like k is less equal the phi of like k is less equal phi of p raised to the like whatever power of prime we have? No, not equal to. We don't have it equal to.
Yeah, of course.
And
Strictly less than.
yeah, exactly. And
The
then
residue
for
set mod P to the K, and then that raised to a fixed, like the power sum of that is
exactly.
divisible by P to the K, right?
Yes, and we like
So
have to consider like p's differently, like power of
yeah,
p's
so
differently.
there are a bit issues with that. We want to go simpler because, of course, once you consider like of the phi of P to the K, it's like P to the K minus 1 into P minus 1, right? So if say K is large, then I can get stuff that is divisible by say P minus 1. But then, as you said, that if I want to do it simply, then this term in the denominator becomes non-zero. So basically, what you said is correct. I'll just keep k less than or equal to p minus 2. And the statement you said is correct. So I'll rewrite it. Also, do you guys know about primitive roots mod prime powers?
Yeah, but could
Yeah.
you like tell me why we need p minus less than p minus 2? Why does not why less than?
As I just said, because if I consider a number like p to the k minus 2 into p minus 1, it is less than what you said, the bound you said.
Huh?
But then stuff like that gives trouble in the denominator. Not for like every prime powers,
Okay,
but
because like we get because it also holds mod p, so it becomes okay.
yeah. We are trying to like easily like make a
Huh.
work. Zero doesn't make a difference. You can see that, but I'll add it because you'll see that like it'll simplify stuff, like make it easier to understand. So p to the k minus one. Agreed. This is what you were saying, Mandar, no?
Yeah, this is what I was saying. But
Yeah.
like also, can we not just exclude the multiples of p minus 1 in M? Like for the choice of M, if we just exclude the multiples of p minus 1, that will be.
Okay. Yeah. Yeah. You probably can, but look, in our problem we won't need it. So
Ah, okay.
yeah, you can do that. Yeah. Remove multiples of p minus one. The proof carries out. So any guesses? I mean, okay, this is maybe a bit involved. So just any thoughts? So this was like this is the build up to this year's India TST Day 3 P2. So yeah, subtle flex. This was one of the good problems that I actually solved in contest.
It was in IMOTC, you said.
What?
Mm, it was in IMOTC, you said.
Yeah, I'm on TST. Any guesses? I just gave a hint that primitive roots also exist mod prime pass and something like induction, of course, because I just proved the base case for you. This is
Yeah,
again, you
so
probably, yeah, don't come up with it in contest, of course. I had seen this before, and you can see how it nicely correlates with the problem. So, yeah. Also, you can probably come up with this in contest, but yeah, it's harder to do that if you don't know it already. It's been used a couple of times before.
yeah, so we know that this sum would like be divisible. No, that.
Also, why are other people not responding? Is everyone not getting it? I can like repeat stuff or go slower.
Could you please explain a bit about the primitive roots modulo p to the power k? Like I
Sure,
just
sure,
know they
sure.
exist.
Yeah, yeah. Oh, okay. Wait, I'll just introduce what a primitive root is mod prime power. I won't give the proof of the existence, of course, but you can see that how this relates to us. So basically, you want a number such that
There is already, uh, sorry, there is already an OMC 2.0 before,
oh, okay,
so
primitive
feel
roots.
free to check that out after this class. Sorry, yeah.
Wait, this problem has been covered already.
No, not this problem, but there has been a class on primitive roots.
Oh,
So
okay,
if you want more practice, you can look at
yeah,
that as
yeah. I'll just state what a primitive root is mod prime power. Anyways, so basically, G is a primitive root mod p to the k if g to the I for I at least 1 and less than equal to phi of p to the k. This precisely generates this set of remainders that are co-prime to p. Yeah, that are co-prime to p. Any doubts? So you know, like also that phi p to the k is precisely the number of co-prime elements. So you can see the connection, right?
Yes, okay.
Yeah. So so the point of primitive roots in our discussion is that you can use geometric series to evaluate the sums, right? So this helps. And you'll of course like if you study group theory and all, you'll realize why like more iteration on this, but I'll skip that. So now try thinking of like break down the problem. So basically, what is the remainder set mod p to the k? It consists of numbers that are co-prime to p, and then there are stuff such that divisible by p, divisible by p squared. So
No, uh,
you see
wait,
that yeah, that might be a way to break down the problem.
so can we like induct on this because we have the base case ready already?
Yeah, yeah, yeah.
And so if we assume that this expression holds till like some p to the k minus 1, then for the next p to the k, we can like divide its what is that?
Like
Remainder set
you
into
divide the
p,
remainder set into elements
p
based on
different
their VP,
chunks.
right? Based on their VP, right?
Yeah, yeah.
Yeah, precisely that. And then you can induct on each of the segments, and then you can multiply that by p to the k minus e if your prime power is e, and then you'll get the
Precisely.
entire thing is divisible by
Divisible.
e to the k, right?
That is what I meant. Exactly.
Okay, I'll just write that down for others. Okay. So basically, you consider the set Sk, which is nothing but remainders. Wait, I think I've used k again. So change e remainders with VP. Everyone knows what VP is?
Yeah.
Yes.
With VP equal E. So, okay, this might be a bit abstract. I'll give an example. So if I consider P squared, right? Like P to the K, if I consider P squared, what are the elements? Elements are precisely 0, 1, 2, P minus 1, and then P plus 1, dot, 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 2P. And then similarly, if you go on, you'll get elements till P squared minus 1. Everyone gets this?
Yes.
So what the set S1 I'm talking about is pretty much the multiples of P in here, which is P, 2P. You get it?
Okay, well.
And the remaining thing
Yes.
you see is co-prime to P, right? In this set.
Yeah, all elements of S1 are covariant to
Yeah, so you can classify
Yeah.
all the elements as like SE forms a disjoint union of the remainder set, right?
Yes.
So now I'll use strong
Yes.
induction. Basically, I'll assume that for the statement for P, K to be true, I'm assuming it's true for till K minus 1. And yeah, so basically, if I compute this sum I'll not use subscripts now. I guess you guys can understand, right? Like if I write I to the K, I'm meaning that I is less than equal to 1, like I is at least 0 and less than equal to p to the k minus 1. Okay, I'm not using subscripts. If you don't get it, you can pause me in between. So basically the thing that I was starting off I to the k, wait, okay, I'm using k again. I to the m. So I'm assuming everything is true till, like for I'm doing it mod p to the k, m is less than equal to p minus 2. I'm assuming the statement is true till k minus 1, okay? Base case is done, right? Just the lemma above. You get it, no?
Yes.
Okay,
Yes.
so yeah. So this is nothing but uh, x belonging to S of, I define it as S of E, right? Yeah, S of E, x to the m, and then I vary like summed over E less than equal to 0 till k minus 1. This makes sense since I just said that SE forms a disjoint partition of 1 to like p to the k minus 1, 0 to p to the k minus 1.
Yes, that one.
Just one thing.
Yeah, yeah.
S0 forms all the means the residues which are not
Co-prime
divisible by
residues,
k,
yeah.
right?
Residues in 0 to p squared minus 1 that are co-prime to p. That is what S0 is.
Okay, sir.
Everyone gets this thing?
Yeah.
Yes.
Okay. So now by induction, if I fix, like, if I look at a specific SC, then what does my induction hypothesis tell me? Okay, first of all, if I look this thing, like if I look at SE more nicely, then this is precisely stuff P to the E time. It is basically P to the E times K, where P and K is coprime, and of course P to the E into K is less than P to the K. Oh no, I'm using the scale. Do I use B? Okay, P and B are coprime, and you get it?
Wait, like it is not. I don't understand what setting could be like. Just
Like this set S is precisely this, no? Elements in the residue set of P to the K, which have Vp equal E.
huh,
So it is P to the E into P, where B and P are coprime, and this, of course, inequalities too.
huh, okay.
I mean, I'm just stating what this is.
Yeah.
Does everyone get it?
Yes.
Okay. Okay, I'll actually write it here. So if you look at it, like if you look at SE, then I should now start to think more like this P to the E is good as a factor, but how does P B vary in this equation?
B varies
Like
from
B
1 to
satisfies
P
this
minus 1.
property that P is less than P to the K minus E, and B is coprime with P, right?
Yeah.
So what is
Yeah.
this?
Pi of p to the power k minus e.
What?
Phi of p to the power k minus e means the
No,
number of p's.
I'm not counting the number. I'm saying that this is precisely what I was looking for. No, this is like S0 for the case P to the K minus E. Like this, you get that this is breaking down the problem. Like these are B is nothing but elements that what are they? They are like the coprime elements to P in the residue set of P to the K minus E.
Yeah, I get that.
You get that? So what does my induction hypothesis tell me?
It tells that for at k minus 1, I would get that sum divisible by p to the power k minus 1.
Wait a second. Yeah. So my induction hypothesis tells me something about this sum of B to the M, right? For this B, which is,
Could you please repeat that part?
yeah, I'm saying. So this SE is nothing but this set, right? I mean, it can be, okay, this is this set, but how is B varying? B is varying like this, no?
Yes.
And so the set of B
Yeah.
is nothing but the coprime residues to P in the residue set of P to the K minus E.
Yeah.
And
Yeah.
that was precisely like, that is easy, no? By primitive roots. Do you see that?
Oh, yes.
Like basically, this sum can be now represented as sigma of G to the M, where G is a primitive root mod P to the K minus E. And then again, you can do that geometric series thing, right? Where you'll
Yes, I
get
get
that,
that.
yeah, phi of P to the K minus E minus 1 minus by G to the M minus 1. Again, this denominator is non-zero and this is 0, right?
Oh, yes, sir.
Does everyone get it?
Yeah.
Please make sure that you get it because we'll be doing this a couple of times in the problem as well.
I didn't understand the summation b to the power m part. How did you get
Okay.
after that?
Yeah, so I'm just no, I'm just pointing out a different sum. You know something about this sum, no? P is this set, and we know from the induction hypothesis about B to the n. Okay, not the induction hypothesis, just look at it like the sum of B to the n. B is stuff that is coprime to P in the residue set of P to the K minus E. You get that?
Yeah.
So
Yes.
what was my definition of the primitive root? Like its power generate precisely that set. So I'm picking G to be a primitive root mod P to the K minus E.
Yes.
And then I can use that geometric series argument I did for the base case, and you will get this sum. Like this is equal to this.
Okay.
Can you convince yourself or
Okay.
like ask any doubt you?
Yeah.
Does everyone get it?
Yeah.
I mean, I can't pause.
Yes.
Yeah, right. So you get that. So now if I sum, so I was summing by, like I was fixing SE and then I was summing X belonging to SE and their power sums, right? So if I compute the inner sum, yeah, like I'm fixing SE, I'm fixing E for the moment and I'm computing X belonging to SE, then X is what? Like this sum is precisely like X to the M is precisely nothing but like P to the E factors out P to the EM, and then this is nothing but, what do you say, B to the M, right? And B satisfies this constraint. Does everyone see it? Was like
Yeah,
SE
now
was
I
precisely
see.
this set, no? SE was precisely this set. No, this was what Mandar was pointing out. You see this? Mm.
Yes.
And I know that this inner sum is divisible by P to the K minus E. And this is of course divisible by EM, right? So the entire thing is divisible by P to the K minus E plus EM. Can you see that this is obviously at least P to the K? So
Oh,
this
yes, I
individual
understand.
sum is divisible by P to the K. Can you see that?
Yeah. Wait, also here we got like K E plus EM. So there should be like some place where the equality holds it, where K E plus EM is K. Like else can we get a like stronger bound?
No,
Right?
of course not. There's always the case of M equal 1. No?
Okay.
I mean, also like the thing where you're talking about, there are all these SEs. So you have to look at the minimum VP. And then if you consider the base case where you're considering only the co-prime stuff, mod P to the K, then you only have that this primitive root argument. It tells you nothing about the VP itself, right?
Yeah, so we can't really like we can guarantee that it is divisible, but not.
Yeah, like I mean, you could say stuff by using LT if M was something, but no, it is not because it is less than equal to P minus 2.
Okay.
You see that?
Yes.
So, okay, so basically you don't have to understand that, but like P to the K divides each individual sum. Actually, also I just said induction, but yeah, it does not use induction. So you see, guys.
Yes, sir.
Okay. So basically, each of this inner sum is divisible by P to the K. So of course, the total thing is divisible by P to the K.
Yeah.
Yeah,
Others
I
also get it,
understand.
no? I mean, okay, you can probably go to that website. Sorry, you can find it on EOPS multiple times. This lemma, you can search it up and then you can like read proofs of like read the proof for like 5 minutes and try to get it if you don't understand it now
What
completely.
is the name?
This is India TST Day 3P2. I think you'll probably find the lemma. Someone would have stated or proved it in the thread.
Okay.
Also, like I'll give you another problem that uses it if psi like creates a
Which
problem
year?
set, then this lemma is actually used. There you'll find a better proof.
You are
So I'll
talking
assume that everyone
which
got
year?
this lemma. This one.
Like the main idea
Yes.
was breaking it into smaller sets, right?
Yes, and where you can use primitive roots. I want only the co-prime bits because primitive roots generate that, and primitive roots have nice geometric series. And their thing is that g to the some power is -1 is divisible, right? So I break it down based on the power of p that divides it. Okay,
Okay, sir.
and obviously the motivation comes from the base case. Base case is rather easy, but okay, it does motivate it. Everyone's fine, no? Like even if you didn't get the proof, you got some intuition. Okay.
Yeah.
So now we'll start off with the main problem, which is, okay, I'll probably write the source. Yeah, problem statements states that if n divides and n does not divide.
It is k to the power 2024.
2 to the power k. A of 2 to the
No,
power k.
k to the power k to the power
Yeah, that is
2024.
k to the power 2024. Sorry. You get it now, no? Does everyone get the problem statement? Like, okay, my handwriting is a bit bad, so ask anything. Also, does anyone see any slight correlation with the lemmas we proved above? This might be a bit intimidating at first, so especially this part, because polynomials are, say, power sums are relatively easy to evaluate as we saw above. So we try to do something with this. So this is the technique that I was referring to as breaking down the problem bits. In fact, you'll see that not just the lemma above, you'll have to break down the problem here again as well.
Then I think we should assume the
ठीक है भाई, ये
contrary
जा
and
सकते हैं.
proceed.
Yes.
I think we should assume the contrary and proceed to prove the divisibility.
Yeah, of course. But like, do you see any relation with the lemma above? Yes. You see any relation with the lemma above? So basically, I'll point it out. But you see this, uh, weird condition prime factor smaller than 2024. Then you see 2024 in the exponent. Does that obviously like this thing p m less than equal to p minus 2 and then m in the exponent and a polynomial thing, right?
Yes.
Right.
Yes.
Yeah. So, but then this is the annoying part. We don't know how to handle this. And of course, even if you try anything around primitive roots, this extra exponent in the exponent does not allow you to compute anything algebraically. You agree with that?
Yeah.
Yeah.
Yes.
Yes. So this thing also points out that how do we use this condition? So I'll try to explore this a bit. So of course, like the easier thing whenever you have been given a divisibility condition is to assume the thing is square free and just start out with a prime factor of p. I have assumed the contrary, so of course p must divide this part, the sum that I wrote. Does everyone agree?
Could you please restate the assumption?
Huh. So 2024 and 2025 are not prime, no. So basically p is greater than 2025, right?
Yes.
I'm saying that if p divides n, then by like the assuming contrary, I'll get that p divides this weird sum.
Oh, yes.
Wait, I'll come back in a minute. Okay. Am I audible now?
Yeah.
Yeah. So basically, this is a trivial thing that you will get this, and then now you start like using this condition that p divides a to the 2 to the n minus a. So see, my motivation was that this a to the 2 to the k is very hard to evaluate. So I try to do something like breaking down this problem. So of course you see that by like there is, do you guys know about orders modulo p?
Yeah.
Yes.
Yeah. So basically, if you see that, of course, I know that this thing will be periodic beyond a point. I mean, if it is periodic, then I can just group terms that have the same a to the 2 to the k, and then I can evaluate this inner thing because I know how to evaluate the inner thing. Like if I
What do
group
you mean
terms
by
that have the
periodic?
same, yeah,
Like how
I,
can we
What do
group
you
terms?
yeah. No, I'm just saying that if I can group things that have the same a to the 2 to the k and vary k, then I probably have a better chance at evaluating the thing, right?
like what do you mean by periodic?
Okay, I'll get to that in a minute. But do you get that if I group terms by a to the 2 to the k, then I can evaluate the inside thing, like probably have a better shot at evaluating that.
Yeah.
Yes.
Yeah. So now I like use this divisibility condition. So when is a to the 2 to the I congruent to a to the 2 to the j? I'll not write mod p. I'll just write p. Okay, you understand that the bracket p implies mod p. Okay. Also, I'll actually use equality from now on. So can you guys come up with a condition?
Like 2 to the I congruent to 2 to the j mod p means.
Can you speak a bit loudly?
Yeah, 2 to the I congruent to 2 to the j mod p means.
Okay, but okay, yeah, that works. No, wait, you're assuming that the order of A is p minus 1. It is only a factor of p minus 1, no?
Yeah, no. Okay, then
Yeah.
we'll like.
Yeah. 2 to the I
Two,
should be congruent
two
to
to
2 to
the
the j mod the order of A, mod p, right?
Yeah.
Does everyone get that?
But why
yes.
shouldn't it be just
Two,
mod p
Yeah.
minus 1?
Yeah. Same thing, no?
Because,
Because
no, it's not the same thing. Of course not. Like,
In the question,
order of A
A
can be less
is
than p
any
minus 1.
arbitrary.
no, because like order divides p minus
A
1 now.
arbitrary integer.
That is not an if and I'm coming up with an if and only if condition. That implies
Okay.
that if 2 to
Okay.
the I is congruent to 2 to the j mod p minus 1, then this thing is equal. But the other way around is not equal. No.
Okay. Like if and only if the order.
Yeah. So you get that this is like agreed.
Yeah.
Yeah. So this is again going to like whatever is smaller. Agreed.
Yeah.
I'll prove that obviously. I mean, can you guys see why this thing is co-prime with 2?
Yeah, like p is greater than 2.
No, I'm saying order of A mod P. Why is that co-prime with 2? Not why P.
Oh,
Use this.
okay, then 2 to the power something would divide 2 to the power something minus 1, which is
Yes,
odd.
right. So you see that this condition implies the above one that odd P A divides A to the 2 to the n, sorry, 2 to the n minus 1. You see that? Because obviously I'm assuming that A is co-prime with P because otherwise we are already done. right? You can see that A is co-prime with P. Otherwise, like you just look at this sum. 2 to the k is a huge number, so P will obviously divide this.
Yes.
So A is co-prime with P, and then you get this condition by just look at it mod P. No? You guys know about this property of odd that it divides like this thing. It's just Euclid's algorithm.
Yeah.
Yeah, so I'll move on. So basically using this, okay, so now what do I do? So okay, it might be a bit complicated, but okay, I'm saying that hard to like right, but I'm looking at okay, I'll actually let this quantity equal J. Oh wait, no, J is being used. T, okay? So I'm saying now I'm considering the order of 2 mod T. So order is obviously defined mod n. It does not have to be prime. It's just Euclid's algorithm. So the properties of order carry over everywhere, right?
Yes.
So basically now what I'm saying T and then I'm again considering the order of 2 mod T. So basically it satisfies 2 to the T minus 1 is congruent to 0 mod T. Sorry. I'm calling this P. So 2 to the P minus 1 is 0 mod T. Agreed. And P is the smallest such number. Everyone gets it?
In the question, excuse
Huh?
me, in the question,
Yes.
A is any arbitrary integer.
No. A is fixed. I'm proving A is a fixed
Oh,
integer. Oh, I'm sorry, I forgot to mention that. Obviously, A is fixed. Does everyone see this? It's like an order of the order. So something of that sort.
Could you please explain it once? Like I did not get the order of the order.
Yeah, so order of P mod A is T, and then I'm looking at the order of 2 mod T. And I call that Q P, sorry, I call that P. So 2 to the P minus 1 is 0 mod T.
Yes.
And then 2 to the N minus 1 is also 0 mod T. This thing.
Yes.
And from the property of order, you'll get that P divides N. It's the smallest. You can just do a Euclid algorithm or just see that it is the order.
Okay, sir.
No, no, no. You get it. No, like just don't agree.
No, yes, I get.
Yeah. So yeah. So this thing is a very helpful condition. And of course, this is equivalent to the entire thing. I considered orders every time. So I'm not reducing any information. I'm not leaving it out. The problem is as it is, and I'm reducing it to a nicer condition. Nicer in the sense that, see, earlier you were able to break down into sets of S, like SE the sets, cause their cardinality 0 to P to the E minus 1 divided the bigger prime power, right? So that's what I meant by periodic, cause now it divides N. So I can actually split it into groups of N by P. I needed that to be an integer. I'll show. I'll show. So basically now I have that the only distinct values that a to the 2 to the k takes the set is precisely this a to the 2 to the 1, a to the 2 to the 2 till a to the 2 to the p. And every time beyond that, and this also satisfies that a to the 2 to the I plus this p is equal to a to the 2 to the I mod p. Convince yourself that, okay, wait, oh wait, shit, I used p two times. Hmm, Q, Q, Q. Can you see that this thing is true? Everyone sees this?
Yeah.
Proceed. So basically what I'll now split it as is something like that. So I'll pair them, not pair them, I'll group them as follows. Like I'll group 1 and then 1 plus q and then 1 plus 2q till 1 plus this q divides them 1 plus n by q minus 1 into q. So every set has cardinality what? N by q. Like this I did for 1. Now I'll just replace this with I. Okay, wait, this is getting a bit messy. So I'm splitting the sets like this. I plus q, I plus 2q, dot till I plus n by q minus 1 into q. For I less than equal to, for I at least 1 and less than equal to q. Do you guys see this? This covers all the numbers from 1 to n.
Yeah.
Does everyone see this? Right? And they have the property, all of them have the property that their a to the 2 to that power is equal by this constraint. Since their differences are q, so all of this set, like if I pick any element x belonging to this set S, then x comma y, then a to the 2 to the x is equal to a to the 2 to the y mod p. You guys see that? They differ by multiples of q.
Yeah, got it.
And you see why that q dividing n condition was important.
Yes, otherwise we won't get integers.
Yeah, of course. And each of these sets has cardinality n by q. It covers the entire set 1 to n. And now the good thing is that this is a complete remainder system mod n by q. You see that again?
Yeah.
So now now can you see that on your own that q is co-prime with p?
Yes, since q is less than p.
Of course, and also because like q divides order of a and then order of a divides p minus 1. So of course p minus 1 is co-prime with p, right? You see that, no?
Could you repeat the last part, like what order?
Right. Q divides t, t divides p minus 1.
Array, हाँ, okay.
Sorry, q divides phi of t. Sorry.
Okay, so basically the order condition that we apply now each time.
I mean, okay, this divisibility is wrong, but you can see that the VP of q, it decreases by at least 1 in these two steps.
Yes, so just that we are applying the order condition twice. That
Yes,
is
yes. Like t divides phi of t and then q divides phi of t. So like the VP of p will decrease by 1 at each step, right?
yeah. Okay.
I mean, okay, I'm saying this because now we are doing with primes. I'll generalize this to prime paths. So then this will be a bit helpful there to see. So, but now it is easy to see that, of course, like q is just less than p. So we are done. But okay, now I'll split it. So I call this sum Si, like I call this set Si, and I'll evaluate it now like this. You see, this is true because all of them have the same value of this thing.
Yeah, got it.
Everyone got it, no? I can repeat stuff like if people ask. Okay, I'll proceed in this. But yeah, so the point being that now I can evaluate this using the binomial theorem. So I'll now fix this I and I'll evaluate the sum for SI individually. So for this thing is nothing but a to the 2 to the I. I'll just leave that out because of course this is the same for all of them. And then I'll have that I to the 2020. Okay, I'll just remove this simplification so it becomes a bit more intuitive. Then plus I plus Q to the 2024 and then this thing 2024. Everyone sees it?
Yeah.
And in this term, if I look at, I expand by the binomial theorem, and I'll get this is nothing but like I to the 2024 n by t times and by cube times, and plus like q to the k, and then of course this uh, I to the k, where I is less than equal to 0 and by q minus 1. Everyone sees this? Okay, I should probably write j. Then I to the 2024 minus k, and then 2024 choose k. This is just the binomial theorem. I'm grouping terms that have the same exponent.
Yeah,
You
could you
see it?
like show the SI definition once? Like
Could you show?
SI definition, SI definition.
Oh, okay, yeah.
Like, I think I messed up something. Huh, okay.
So you see that this is true, no?
Yeah.
Like I just took this q, factored it out, k, and then this j was like basically 0 to n by q minus 1. You see it, no?
Yeah.
Yeah, and basically, as I said, p divided n by q, because I said that q is co-prime with p, and p divided n. See that?
Yeah, got it. Like just
Yeah, so
binomial.
basically 0 to this forms n by pq residue systems mod p. Like it is 0 to p minus 1 and then 0 to p minus 1 n by pq times, right? Like, okay, convince yourself. Like, I can pause for a 30 seconds or something.
Oh, so like firstly we had n by q and then like we are
Yeah, p
going from
divided
0
that,
to p minus 1.
p
Like
divided that. Yeah, and then basically I have numbers from 0 to n by q minus 1. They pretty much form a residue system. They are like n by q terms, n by q consecutive numbers, right? This thing.
got it. Okay.
And each of them form like a residue system mod p, since p divides that. So
Yes.
I
So we
can
get
split
like
them
p
again
residue
into groups
system.
of, yeah, I can split them again into groups of p.
Yeah.
And then I use my lemma, the first one. I know that each, like the power sum for each residue system mod p is divisible by p. And I have an integer multiple of those many residue systems. So this thing is still divisible by p. You get that? It is basically a residue mod p. Mod p, this is just a residue system copied n by pq times. The power sum for each of these systems itself is divisible by p. So the thing is divisible by p. Do people follow?
So n by pq is integer, so it follows.
Yeah, that's my
Okay. Okay.
yeah. So this part is divisible by p because of course as I pointed out, this is divisible by p. So this entire thing is divisible by p. And this is divisible by p because n by q is divisible by p.
Got it.
So so basically for each SI, this entire thing is divisible by p. If I sum over all SI, this entire thing is divisible by p.
Yeah, got that.
Yeah. So now the thing is key, okay, this worked, but of course, n is not square free. Like it can have prime powers as factors as well. I just wanted to show you like an easy case to motivate this. This is how I approach the problem as well. And then now I should strike that probably that lemma can come in handy because maybe the arguments I did for P, they lift to P to the K. This is how like this is the strategy we start off with. This was pretty simple. This was divisible, and this I used the simpler lemma to just compute since it's okay. Also, like guys, get comfortable with this thing that if P divides n, then the numbers 0 to n minus 1 form multiple residue systems mod P, an integer multiple, right? They are just consecutive numbers.
Yeah.
Okay, so I just use that fact and the fact that each of the power sum itself, and that of course that k is less than equal to P minus 2, since the original constraint I had assumed the contrary. And I just used my lemma multiple times and got this thing that this is divisible by P.
Yeah. So like generalization also will be like induct somehow that we didn't.
No, wait, yeah, actually the generalization is a bit non-trivial. Like it's not easy. Like okay,
Okay.
so also is everyone comfortable? Because I see a lot of people leaving, so I might skip the problem. Like this is intuitive enough to like give an idea of how powerful the lemma was. So do we want to move to something easier?
No, like we made it this far, 15 minutes of the class.
Okay, okay, yeah. So now we do the argument that P to the K divides N. And then I repeat that order argument because orders are always existing. They don't need to have primes or stuff, right? It's just the Euclid algorithm. So I'll carry over the same notation so that it makes more sense. So I let this be T and I let that be Q. So I'll just consider this the order of A mod P to the K. I call that T, and then I call the order 2 mod T to be equal to Q. Do you realize that if and only if condition carries over to this, it had nothing to do with primes,
Got
just
it.
Euclid algorithm. The same condition carries over, and even I can just consider the same splitting SI. Do people follow? Because the thing is again an integer.
Yeah.
And that is why I'm like, I have to prove that why is it an integer. So because I have this condition that Q divides phi of T and T divides phi of P to the K. So T has VP strictly less than K. You see that? Because it is P to the K minus 1 into P minus 1. Of course.
Yeah, got that.
And then phi t never increases the VP, it can only decrease it. So Q can have VP like less Q VP of Q is always less than equal to K minus 2. Do you see that?
Huh.
Everyone sees that, no? Okay, I'll just
Yeah.
continue. Just like
Yeah.
we'll get done with this problem quickly. Actually, I think many people are not following. So with this condition, I still have that ny,
PQ.
yeah, pq. Yeah, of course. Ny pq is an integer because the denominator has VP less than equal to K minus 1 and n has VP at least K, right?
Yeah.
So this is an integer and I'll just consider the same SI. I won't repeat what SI was. SI is the same here. Look at it. Probably note it down if you have a copy or something.
Got it.
Yeah. And yeah, I'll just carry this over. And then I'll again evaluate by binomial theorem. So I'm evaluating the SI, not the entire sum. I'm fixing, like I'm looking at SI first, and then I'm doing something similar to this. Okay. So it's pretty much again I to the 2024. Wait, I don't have to do a same condition here. Yeah. It's like I to the 2024 times n by q and then plus. Now I'm fixing k. Okay. So I'm fixing k like basically the expansion of binomial theorem from k like 0 to 2024. So k is so I evaluated the k equals 0 term here. This is the k equals 0 term. This is just the binomial theorem. You can maybe verify the calculations later. But yeah, this is at least k is less than equal to 1. And of course, this and by
Q minus 1.
q minus 1, right? So if I fix k, then q to the k terms come outside. And this is nothing but again j to the k, where j is varying like this. Everyone is convinced. There is the factor of probability for choose k, which I won't consider because it doesn't affect mod p. I mean, I'm ultimately proving divisibility anyways.
Yeah.
This is the thing we have. Now try to use the stronger lemma. Also, I'll probably like let Vp of Q explicitly E, and then E is less than equal to K minus 2, so that you can probably like explain it to me a bit easier. Do you guys see, or should I explain?
Like just
Yeah, okay. Do people see it? Your U is varying from 1 to 2024. Basically, binomial theorem. Mandar or anyone, you like unmute.
no, I don't see it. Like this term, the second term is okay, just by the larger lemma, but the
Oh,
first
right.
one,
No, I'm not asking you to look at the first term. That is the like the thing of the problem. You see that this is divisible by p to the k, no?
that is divisible. The
Because
second
this
part
is
is not.
divisible by p to the k minus e, and then this is plus eu, right? Because this
Yes,
has vpe. So this is always at least p to the k, right?
yeah, that
Yeah, so
is.
that was the major part. Now look at something special about this thing. I'd also write a to the 2 to the I, because everything was always multiplied by that. So now see, what is the vp of n by q?
K minus E.
K minus e, right?
Yeah,
Yeah. So it suffices to prove, like this is equivalent to proving. Do you see it? Sorry. Wait a minute.
okay. So like we grouped these other terms together, which were like
Yeah,
n
yeah,
by
yeah.
q.
We grouped them by a to the 2 to the I. This stuff was
Huh.
like always divisible by p to the k, so we just ignore that. This is what caused it problems. This was still divisible by p to the p to the k minus e. But to finish the problem, it would suffice to show this happens, right? If
Yeah.
p to the e also divided this thing summed over
Yes.
all I, and I is pretty much like 1 to q, right?
Huh.
Does this thing now remind you of something recursively?
This is like the original problem. Now, this is what
Right.
we assumed for contradiction.
No, wait, we didn't assume this for contradiction. This is something similar to that. That
Huh.
was still n. We reduced the problem. So I could like do the same thing again, if which condition was true?
If the a to the 2 to the n minus k wala condition.
Yes, right. मतलब अगर वो होता like a
हाँ
to the 2 to the q minus a was divisible by p to the e. Not this is not the problem statement, but I'm saying कि हमने तो इतना ही start किया ना, like we just started off with this.
हाँ
So if these two conditions were true, I can like continue with the same thing, like order ka order, and then that
हाँ
divides the entire thing, then split it like this, and then continue recursing. So if
yes
these two statements were true, I'm back to square one, right?
yes.
But now I've reduced my power of e.
So we can keep reducing power of e,
Yeah, and
like
this thing is obviously true. You see
yes.
it, no? This thing is true because that is the
Like
definition.
yes.
And this is the like I can now continue with the same thing, except my e is reducing by at least two at each step.
Okay, because that k minus 2 wala like 2
Yes,
times
that
5
k
thing.
minus two.
Okay.
So it is reducing
Huh.
by at least one or at least two, whatever. But I
Yep.
can continue repeating this until I get that p ka power k actually divides this thing I started off with.
Yes.
So that is the contradiction. So if every prime power of n divides the sum, then n also divides the sum. But we started off
With
assuming
n
the
not
con.
dividing the sum.
Yeah, that was the condition.
Nice.
So you see, like we are basically breaking down the problem multiple times. First is when we use the lemma, we broke it down into sets like p to the e, and then now we use the order condition, and then we break it down again into sets si, and then after that we again break it down into multiple residue systems where we use the fact that p divides n by q. We broke it down again, and now finally we broke it down when we saw that this is pretty much the original problem.
Yes. Wait, could
So
you
this
like
is
just go over the last thing? Like we have reduced it to the smaller one, then
yeah, but so the condition I reduced it to was p to the e dividing this thing, and
uh,
e is less than equal to k minus 2.
yes.
So if I
So
repeat
we
the same argument, I'll probably like get another, I'll probably get another e1 such that the condition, this thing is equivalent, this thing now is equivalent to this thing, p dividing a to the 2 to the I, and I to the
okay,
2024, and then I less than 1 less than
so it
q1
is
for some q, and then p to the e1 also dividing a to the
yeah.
2 to the
So,
q1 minus a. And
so
q1
is
and
it
e1 are
something like
strictly, q1 and e1 are strictly decreasing.
yeah, so we will eventually get like some
You'll
p which
eventually get
divides
something
it
like
and hence
one divides,
everything is true.
you'll eventually get one divides the thing.
One divides the thing and then n divides it, which is contradiction. Okay.
Right. Which is so like you prove the original thing is true because these were if and only if statements.
Yeah.
So
Oh, that
basically
is why
all
we
prime.
needed the order thing and not five. If and
Yes,
only if.
right.
Huh.
Yes. Because otherwise you cannot necessarily split it into like, and you also need to ensure like you can do that there, but here when you have to see that n by q is also divisible by p, that is the harder thing.
Yeah. That was
So do you guys have energy left for another problem, or we'll probably end now?
yes.
What like energy for another problem?
Yes.
Okay. Wait, I'll ask Sai actually. Sai, are you there? Yeah, of course. Um, okay, so I'll use this trick. We'll see this technique. It's called like whenever you encounter things like say proving a set has infinitely many prime divisors, you yeah you'll encounter this a lot in int poly, but I'll not go towards int poly. I'll consider a different set for now. So suppose that AI is an increasing sequence of naturals, BI is an increasing sequence of naturals, then prove that the set AI BJ plus 1 has infinitely many prime divisors. So the trick that we use, I'll actually spoil it to you because we don't have much time left. So this thing is we use something of a maximality argument on largest prime power or bounding VPs basically. Yeah. So anyone has any idea on this thing, this set? At least you got the conditions, right? AI is
Yeah.
increasing, BI is increasing, and then this set AIBJ for all IJ in naturals, the infinite set has infinitely many prime divisors.
Yeah.
So often the thing that, so can you see anything that is nice with this, like with this set? This plus one ensures some sort of coprimality condition, right? Like if P divides this, then P cannot divide AI or PJ.
AI will be yeah.
Yeah. So actually, you'll see this argument in an INMO problem as well in 2019. Means slightly different. It was actually different, but this is, say, a better version of the thing. So I'll explain the intuition to you. When you have finitely many primes, if you can bound the largest VP of the term, right? Absolutely. Like, then it's just a finite collection of primes. So each prime power is bounded. That means the terms are bounded. But in our case, that cannot happen since AIBJ is a strictly increasing sequence of positive integers. So you get the rough idea. I mean, it
Yeah.
happens in case of polynomials as well or other sequences, any sequences. You also have Kobayashi theorem. It has a like a special case of it has a similar proof. Also, this is true by Kobayashi's theorem, but you cannot state that anywhere. And this proof is also much more intuitive.
Wait, why
It's,
can't we state Kobayashi?
because its proof is non-elementary.
What?
But like, how can you say Kobayashi? AIBG doesn't necessarily have like a finite necessary finite
No,
number.
I mean it's not obvious. You have to do that twice, but I'll not go that way. You can probably search this up, okay, if you are interested. So let's do this thing. So if I say for a moment I fix J. Okay, I'll type it after the end of the lecture. Just remind me. Okay, yeah, that is the name. So say I vary I, but I fix J. I1 and AI2 BJ plus 1. So is there anything nice with the difference? Now I'm talking about
Divisible by
differences
VG.
because you probably know that if like prime VP things are nice with differences because the minimum VP is the VP of the difference, right? Like
Yeah.
the VP of that is at least the minimum of that, right?
Yeah.
So if I consider the difference, J, okay, wait, actually J1 and J2, but J1 and J2 is belonging to a bounded set. AI1 is varying infinitely, right? So you get the difference. Okay, actually, I'll write this as AI1. Then you factor this out as BJ2 and minus BJ1. So if this thing is bounded and if a prime divides both of them, prime divides this, all of you all agree?
Yeah.
Prime cannot divide this, as I just stated, because of this plus one.
Huh.
So, I mean, not a prime power also. Okay? So, prime power must ultimately divide bj2 minus bj1. You all see this?
Yeah.
So, if the j1s were belonging to a finite set, then this difference is bounded, right? Which means that the prime power is bounded.
True.
I mean, I am varying I1 in an infinite set, but GIs are in a bounded set.
Yeah. So like in some sense keeping AI like BI
Yes,
constant and then
yes, AI
other thing.
constant and varying BI, but AI is also varying eventually. I mean, okay, it's a bit hard to state in words, but
So
yeah,
you're like
I1
saying
is
that
large. I1
for
is large.
some AI we are like keeping the set of BIs small.
Yes, exactly, small. Yeah. So that would give a bound on the P to the K because these are just finitely many terms.
Okay.
So do you want to think or should I just reveal the idea?
Now wait like 2 minutes.
I'll wait for a minute. So yeah, and PHP. Yeah. Do you guys need more hints? Just read the heading again.
Wait, is it something like we know that it is like vi is bounded and like ai is varying infinitely, so the numbers just become as large as we want, but then the vp is bounded for each prime.
Yeah, but you have to justify why P was common for both of them and why like the other primes also have a fixed like a bounded VP. This is just any random P. I was just giving an example for a common prime factor. Like, I mean, the intuition should be clear after this argument. This is a bounded thing. This must be bounded. So overall, the thing is bounded. I just have finite many primes.
Yeah.
But like, how? So that is where you have to use a maximality argument. Okay, I'll probably reveal it. I mean, it's a good thing to know in mind. You'll find many problems that do something like this. So I'll consider for each term like this, like AI and okay, like AI bj plus one. I'll assign it to a prime pi comma j. And of course, the set of primes is finite. Everyone sees that because I'm assuming the contrary.
Yeah.
So I'm assigning this prime such that this prime has the largest VP, not the largest prime power. It has the largest VP. So it can be a smaller prime, but it has the largest VP. Does everyone see that?
Yeah.
Okay. So now if I like fix I and I consider P1, B2 till and say that the cardinality of the set of primes is K and BK plus 1. So what does PHP give me?
One of the prime occurs infinitely often.
Yes, it must be equal to, right?
Huh.
Like basically you get that Pi comma
Like many of the primes are
J1
just
is
equals.
equal, yeah, right, is equal to Pi comma J2, where J1 and J2 belong to the set 1 till K plus 1. Okay.
Yeah.
And then, but I can vary I, right? Always remember that. B's are bounded, I'm varying I. So basically with that, let's call that prime P, okay?
Hmm.
Then I consider P to that VP thing. So I'm not writing, but K is nothing but the minimum of VP of these two terms. Okay, I'll
Yes,
call
the
it.
difference wala.
No, not the difference one. Individual terms. Like I'll write T to be minimum of VP of uh, AI comma BJ1 plus 1 and then VP of AI1 BJ2 plus 1. Do you see that this, then I'll have that P to the T divides BJ1 minus BJ2.
Yeah.
Because I know I just stated that the if like the difference of two numbers is divisible by P raised to the minimum of the VP of the individual numbers. That is like well known thing. No? It's
Huh.
obvious as well. So you will have this condition that P to the T divides it. But then notice that Pj1 minus Pj2 is a bounded thing. Like I consider all such pairs, all such what do I have? Yeah, K plus 1 choose two pairs of J1 J2. They are that is a finite set. So this thing is absolutely bounded by a big constant C, right?
Yeah.
That means that P to the K is bounded by that big constant C. which means
Okay.
that K itself is bounded by log 2 of C. I mean, cos C, the bigger the prime is, the log is the smaller, right? So,
Okay. ठीक है.
I mean, this is, okay, I'll just write it. This is greater than 2 to the K.
This
So, K
okay.
is less than log 2 C, right?
Huh.
So, but now K was what? Oh, fuck, man, I'm writing this.
Christina, T was minimum of those.
Yes, but no, for the individual terms, what was it? It was the largest
It was the
VP,
largest one.
right? So if I let the, like, I had considered this set of primes P. So if I let Q be the product of the elements, let's set P, product, oh wait, product headed by notation, I of P belonging to this capital set P, and then product of these primes, then I'll have that, this term, like the one that achieved the minimum, say without loss of generality, T was the VP of this, okay? You get that?
Yeah.
Then I'll have that Q, that AI bj1 plus 1 is strictly less than Q to the T.
Okay, because it contains that.
And this
ठीक है.
is less than Q to the, say, kuch bada number into log 2C. But this is absolutely bounded, right?
Yeah.
However, if I vary I, they both were increasing sequences. So I is an increasing sequence. This cannot be absolutely bounded.
Okay, and hence it has infinite time.
Yeah, so hence it has an infinite number of
Huh.
set prime factors of the set. So there are two important things to keep in mind. So often you can either consider something like the largest prime power, not necessarily the one with the highest VP, the one with the largest prime power, like say in the set 2 squared, sorry, 2 cubed into 3 squared. So I'm talking about 3 squared, the largest prime power, not the one with the highest VP. So that argument also helps sometimes. And this might have, I modified that to suit this. So here I'm considering two actually, because 3 is bigger than 2. So you got the example, okay, like just ignore it if you didn't get it. So those are two types of things you can do to bound VPs. There are like many much more interesting problems of the form that you have been given an infinite set, you have to prove the prime factors are infinite. So yeah, often this PHP and then sort of bounding the VP helps a lot. So this was one technique. So I'll probably like, we can end the lecture today. And can you guys give me feedback? Like I see that this lecture was a bit maybe rushed for problem two because I wanted to end that early. So, and maybe a bit higher than in Moon.
Could you give the Kobayashi proof for this?
This one. Okay. I actually forgot that myself. Yeah. I mean, I just read in the thread, someone wrote Kobayashi. I didn't really think about it. It's not obvious, of course.
Could you send the thread?
You can, okay. Yeah, I'll send the thread in the OMC server. So, guys, any feedback?
No, the class was nice.
Okay, but okay, let's see. And don't call me sir, bro. Like, you can just call me bro or something.
Exactly.
So,
You're not old.
yeah, bro. Sophie reference, bro.
Yeah.
Yeah. Any other feedback? Also, like, thank you guys for attending. It was a bit maybe intense towards the mid part of that. So, Sai, we can end the lecture maybe.
Like, wait, random question. Why can't we use Kobayashi? I've been spamming it like in all exponent entities, I see.
Because the proof is non-elementary, right? They won't give you marks for that anymore if it ever comes. I mean, it
But
did come in 2019.
exactly. Kobayashi
I
did
mean,
that as
okay,
well.
no, Kobayashi didn't come, but like if you didn't know this trick then or something of this sort, then it's probably a bit harder to come up with. But this PHP thing and like a finite set of primes and then the max BP or the largest prime power is a very helpful thing to analyze.
Can you even can you use like Kobayashi in TSTs?
Probably, but they won't. They actually give instructive problems, like not things that can be nuked with a statement. But yeah, in
Yeah.
TSTs, everything is allowed.
Can we use Dirichlet's theorem in INMO?
Wait, most of the times you will be using like that sort of NT comes in Iran contests the most. I was planning to cover a problem, a very nice problem of that sort as well, but we ran out of time. So,
Is
but yeah, I'm telling that the proof where you consider primes mod 1 for some n, that can be proved by cyclotomic polynomials. That does not require
yes.
Dirichlet's theorem. So that you can probably state. I'm not sure, but you probably won't need it
Mm.
because InMode doesn't have those sort of problems.
Does the
Oh,
Dirichlet have an elementary proof?
No,
no,
of course not.
it
I
has
mean,
no known elementary rules.
you can prove like infinite primes mod 1 and minus 1 elementarily. Like you
Yeah.
can just consider that Chebyshev polynomial and cyclotomic polynomials.
Wasn't
That's
there
an
proof
algebraic
from
guarantee.
quadratic residues?
What?
There's also proof from quadratic residues.
Quadratic reciprocity, right? It does use that.
Yeah, like most of the time, cyclotomics and quadratic reciprocity just go in hand. Like you can
Yeah,
just
right. It
match
finishes
them.
it. I was planning to cover a very nice problems, like two problems of that sort, but we ran out of time. Maybe some next time, if you guys are interested, I'll take a session called Spam Anti. It appears
Huh.
a lot in Iran contests. Like basically, you have to do a bunch of CRT, bunch of Dirichlet, and like use LT and every sort of fun stuff. So
Yeah,
it's like very interesting.
exactly. Like those are like
But
very
again,
scam
yeah,
problems.
yeah, they are satisfying, bro. But the thing
Huh,
is that they
exactly.
might be not relevant to Indian contests.
No, they won't. They probably are not relevant to any other contest other than Iran.
Yeah, right, agreed.
Yeah, like, but they're very fun to just spam.
Yeah, and Elmo, because Elmo is a troll contest. But
Huh.
yeah. So any other doubts or any other reviews or feedbacks?
It was a good class. Like, could you give me like some good problems, like
Yeah,
the
of
way
course,
you
I'll give you
discuss?
that famous USA THTST problem that uses both the lemmas that I was talking about. And then, yeah, I'll give you that local arguments problems that I was talking about.
Okay, okay. Like, could you just tell me one or two? I'm just bored. I don't have anything to do.
Okay, so you can probably, it's called USA TSTST 2019 P2 or 2018 P2, the one with which you had polynomials like x plus somethings to the power something.
Okay, okay,
Yeah, you can probably find that. Did anyone
okay.
raise their hand or something?
No, like
Cool.
I don't think anyone did.
Sai, did she leave?
Yeah,
One
Sahi is not here.
check
So
DM.
okay, I can stop the recording as well. Okay. Yeah. So bye guys.
Yeah,
Hi,
bye,
thanks. Manda,
bye.
check DM.
Okay,
Thanks.
okay. Yeah, bye.